This video promises to be a very short one because this homework assignment, homework 17, period and frequency, covers a very, very small set of principles. It's really just tooling us up to do the more interesting stuff in circular motion. The idea is that things go around in circles, and when they do, they have speed. Speed is distance over time. That's how we defined it when we were first doing kinematics, distance divided by time. But when an object goes around in a circle, the distance that it travels is the circumference of the circle, 2 pi r. And then it repeats that circumference over and over and over again. So motion, circular motion, is periodic motion. It's motion that repeats in time. The amount of time that it takes to go around once is called the time period of the motion. That's why it's given a capital T here instead of a lowercase t. Nobody should ever mistake this capital T for the tension in a rope, because we should recognize the relationships and their meaning here. So the velocity of circular motion is 2 pi radius divided by the time. As always, when I'm doing my physics, I should use the radius in meters and the time period in seconds. When we're solving problems of this type, we very often encounter frequency, which is the number of revolutions in a certain period of time. We often encounter the frequency in the form of RPM, revolutions per minute. Some people may even recognize this from the dashboards of automobiles, where the rate at which the rotating parts of the engine are turning is reported on the dashboard as RPM, revolutions per minute. Well, revolutions per minute won't do for my calculations. What I need is revolutions per second. Well, if you think about it, if there's a certain number of revolutions per minute, it's going to be a lot of revolutions. In 1 second, it will do fewer revolutions. So as conversion factors go, it's very sensible for me to divide by 60 here, because there are 60 seconds in 1 minute. If I take the revolutions per minute and I divide it by 60, then I get the revolutions per second. I might call that RPS, revolutions per second. It turns out we don't do that. We write it as 1 over seconds. I personally like to write it as seconds to the -1, and sometimes this is called hertz. So there's a little bit of getting used to the lingo here with the symbolic notation, but frequency is the number of revolutions per second when done in SI units. It's simply related to the time period. If you know the frequency, then the time period is 1 over the frequency. If you know the time period, the frequency is 1 over the time period. They have an inverse relationship, and that means, that relationship being so simple means they're often used in common ways. You'll also want to be careful about the distinction between diameter and radius. You already know that diameter and radius are not the same thing. When I say that the speed of circular motion is 2 pi r over the time period, that r is the radius of the circular motion. And then every once in a while, these problems that we get assigned, they like to trip us up by giving the diameter as kind of a gotcha. When I'm given the diameter in a problem that I'm solving, I want to divide the diameter by 2 to make sure that I'm using the radius. Otherwise, my answer is going to be off by a factor of 2. It also happens in this particular homework assignment that once again, a problem is asking for an acceleration expressed in terms of g. It's not the first time that's happened. It happened back in kinematics. It's very simple. Simply calculate what the acceleration is, probably by using the speed squared divided by the radius. And then once you have that acceleration divided by g is going to be the acceleration expressed in g. It's almost treating g, 9.8 meters per second squared, like it's a unit, the acceleration in g's. The last 2 problems of the assignment are arguably the most challenging. The first one has us describe the motion of the Earth around the Sun as circular motion. The orbit of the Earth around the Sun is in fact elliptical, as we'll see in the lectures coming up this week. But we're going to treat it like it's a circle of a known radius. In fact, the radius is given in the problem 1.5 times 10 to the 11th meters, the radius of the Earth's orbit around the sun. And I know the time it takes for the Earth to go around the sun. That's 1 year, 365 days, with 24 hours in a day and 3,600 seconds in 1 hour. If I have the radius in meters and a year's worth of seconds, calculating the speed that the Earth goes around the sun, is no trouble at all. I don't actually know what the answer is, but you're looking for something that's somewhere around, I guess, around 20 kilometers per second. And then once you have the speed, the acceleration is easy to calculate. You just take the speed squared, the speed that you just calculated squared, divided by the radius. In the final problem of the assignment, your roommate has a bike, apparently, and the bicycle tire is spun around. There's a pebble stuck in the tire, and you see that pebble going around, going around, going around. You observe that it goes around a certain number of times per second. I guess part of the trick of this problem is realizing that that number of times per second is the frequency of the tire's rotation. Once you know the frequency, you can calculate the speed of the rotation of the edge of the tire simply by doing 2 pi r over the time period. But here we have the frequency. So I suggest a little modified version of the equation, that the speed of the circular motion is 2 pi r times the frequency. You have to be careful here because this is one of these little tricky cases. The diameter of the tire is given, not the radius. So naturally you have to divide by 2. So 2 pi r times the frequency, all of that information is given. Radius you're going to do in meters, frequency you're going to do in per second, and then you have the speed. Once you have the speed, calculating the acceleration is easy. It's simply the speed squared divided by the radius, according to our centripetal acceleration law.